Okay, question 5, continuing. This is a very standard question. We'll take the auxiliary equation, which is lambda squared plus 2 lambda plus 10 equals 0. Solving this by completing the square gives you lambda equals minus 1 plus or minus 3i. So the complementary function is y equals e to the minus x c cos 3x plus d sine 3x. We don't have to worry now about the particular integral being part of the complementary function, so we can just let y equal a cos x plus b sine x. Differentiating gives you a minus a sine x plus b cos x, and differentiating again gives you minus a cos x plus b sine x. Substituting this into the differential equation gives you minus a cos x minus b sine x minus 2a sine x plus 2b cos x plus 10a cos x plus 10b sine x equals 85 cos x. Combining the cos x's gives you minus a plus 2b plus 10a, and combining the sine x's gives you minus b minus 2a plus 10b. Then we just compare coefficients of cos x and sine x, so we get 9a plus 2b equals 85, and 9b minus 2a equals 0. Substituting b to be 2a over 9 into the cos x equation gives us 9a plus 4a over 9 equals 85. This means that 85a over 9 equals 85, so a is 9, and b is 2. This means the general equation, which is the sum of the complementary function and the particular integral, is just y equals e to the minus x c cos 3x plus d sine 3x plus 9 cos x plus 2 sine x. Okay, moving on to the penultimate question 7 of 7. So, de Moivre's theorem. Consider cos 6 theta plus I sine 6 theta, which is the same as cos theta plus I sine theta to the power of 6. Expanding in the usual way using binomial expansion and replacing cos and sines by c and s's for abbreviation purposes gives us c to the 6 plus 6i c to the 5s minus 15c to the 4s squared minus 20c cubed s cubed plus 15c squared s to the 4 plus 6i c s to the 5 minus s to the 6. Now sine 6 theta is the imaginary part of this, so we just take the imaginary parts of the expansion, which gives us the following terms: 6c to the 5s minus 20c cubed s cubed plus 6c s to the 5. Taking out a factor of cos theta gives us 6 c to the 4. C to the 4, or cos to the 4 theta, is 1 minus sine squared all squared. And then c cubed, or c squared theta is going to be 1 minus sine squared theta. And s to the 5 doesn't change. Expanding the first term gives us 6 sine minus 12 sine cubed plus 6 sine to the 5. Expanding minus 20 brackets 1 minus sine squared times sine cubed underneath gives us minus 20 sine cubed plus 20 sine to the 5, and then writing 6 sine to the 5 theta here. I've written it like this so we can do column addition in the obvious way, giving us 6 sine theta minus 32 sine cubed theta plus 32 sine to the 5 theta as required. The next part asks us to consider sine 6 theta over sine 2 theta, where sine 2 theta can't be 0. We're going to use sine 2 theta equals 2 sine theta cos theta. I'll replace the numerator of sine 6 theta by the expansion from before, giving us c brackets 6 sine theta minus 32 sine cubed theta plus 32 sine to the 5 theta all over 2 cos theta sine theta. Dividing the numerator by 2 and cancelling a cos theta and a sine theta gives us the following expression: 3 minus 16 sine squared theta plus sine to the 4 theta. Now, we need to maximise and minimise this, so a sensible thing is to think, how can I find the roots? The most sensible way to do this is to complete the square. So if we complete the square, we get 16 brackets sine to the 4 theta minus sine squared theta over plus 3 over 60. Completing the square inside the bracket gives us 16 brackets sine squared minus a half all squared minus a quarter plus 3/16. Expanding and simplifying gives us 16 sine squared minus a half all squared minus 1. Now if we consider sine squared minus a half all squared, this has to be bigger than or equal to 0. If this is bigger than or equal to 0, then the smallest value our expansion can take, or sorry, our expression sine 6 theta over sine 2 theta can take, is going to be negative 1. Because sine squared minus a half all squared can't be smaller than 0. The next thing to consider is the maximum value of sine squared minus a half all squared. So sine squared, its biggest value is 1, so 1 minus a half is the biggest value in the brackets. A half squared is a quarter, so this is the maximum value. So this means that sine 6 theta over sine 2 theta must be less than or equal to 16 times a quarter minus 1, which is 3. The only thing now left to do now is to consider why is the inequality strict here rather than less than or equal to. Well, if sine squared is equal to 1, which is its biggest value, then we can say, well, what if this means that one of the values for theta would be pi over 2? Because then sine theta could be plus or minus 1, one of the values of theta would be pi over 2. But if sine theta is pi over 2, then sine 2 theta is equal to 0, which is no good since sine 2 theta can't be 0, so this would be a contradiction. So therefore the inequality must be strict. Okay. The final question. Using Dumar's theorem for tan this time, so we'll replace tan 4 theta by sine 4 theta over cos 4 theta. We'll need to consider cos theta plus I sine theta all to the power of 4 using Dumar's theorem. This expansion is cos 4 theta plus 4i cos cubed theta sine theta minus 6 cos squared theta sine squared theta minus 4i cos theta sine cubed theta plus sine to the 4 theta. The numerator of sine 4 theta is going to be the imaginary part of the expression we've just written, which is 4 cos cubed theta sine theta minus 4 cos theta sine cubed theta, all over the real part of that expression, cos 4 theta minus 6 cos squared sine squared theta plus sine to the 4 theta. Now, if we divide top and bottom by cos to the 4 theta, you get the expression you want, 4 tan theta minus 4 tan cubed theta, all over 1 minus 6 tan squared theta plus tan to the 4 theta. So that was dividing top and bottom by cos to the 4 theta. Part 2. Okay, so this says find the exact roots. Now notice it's slightly different to questions we've done in class. It's a bit easier. It doesn't say find the exact values of the roots. It just says find the roots, find the exact roots. So for part 2, we need to use part 1. So if we write down the expression again, we'll need to get the numerator on one side. So if we add 4 root 3 tan theta and minus that 4 root 3 tan cubed theta from both sides, we effectively get the numerator. Not quite, we're a factor of root 3 out, but that's fine. So now if we divide both sides by tan 4 theta minus 6 tan squared theta plus 1, we'll get the following expression, or equation rather. 1 equals 4 root 3 tan theta minus 4 root 3 tan cubed theta over 1 minus 6 tan squared theta plus tan to the 4 theta. This right-hand side is now root 3 times by tan 4 theta. Okay, so this means tan 4 theta is 1 over root 3. So this means that 4 theta, using our special triangles or your calculator, is 30 degrees or pi over 6. And to get the other values, we'll just add pi to them. So we'll get 7 pi over 6, 13 pi over 6, and 19 pi over 6. So there are the 4 roots for tan 4 theta. So theta, therefore, is pi over 24, 7 pi over 24, 13 pi over 24, and 19 pi over 24. This means that the roots of the equation that we're asked to find the roots of are just tan of pi over 24, tan of 7 pi over 24, tan of 13 pi over 24, and tan of 19 pi over 24. That's it. That's all the roots. It didn't say find the values of the roots, it just said find the exact roots. And there they are. Okay, so that's the final question from the mock. Hopefully, having gone through these, you can see that they're actually not too challenging. Okay, see you in school.